Okay, so let's get started. So here we have our 26th HKU IDS Scholar Seminar Series. And today I'm happy to introduce Professor Qingpeng Zhang. He's an associate professor at HKU IDS, as well as the Department of Pharmacology and Pharmacy. In his seminar today, The Predictability of Complex Systems, a Statistical Physics Approach to Understanding Prediction Limits, will present a statistical physics framework for understanding the theoretical limits of prediction in complex systems, which will link machine learning problems like binary classification and link prediction to spin glass models. So without further ado, let's welcome Professor Zhang.
Okay, thank you, Alec. Thank you, everyone, for coming. So this is actually the very first time I present this topic. See that I'm now in the medical school, so usually we present something about our precision medicine or drug discovery research, but still we have a small track in our group to delve into the theoretical complex systems. And this is a paper that we just published, and I just finished these slides 5 minutes ago, so bear with me if I'm not quite fluent during the presentation. But predictability, first, complex systems, right? So what is a complex systems? So a complex system in physics usually indicates a multi-body systems. That essentially means that it's hard to analytically derive something from this system. So we have to rely on some statistical properties. So just imagine that if we're talking about a link prediction problem, if we want to know that which one of you, which two of you actually have the WeChat group, WeChat friends, right? So to predict individual cases is difficult, but to predict the whole population's behavior from a statistical perspective, it becomes a little bit easier, right? So we rely on those statistical patterns to characterize the whole system, to analyze dynamics, and to seek the opportunities to control, right? To observe, control the system. So here we're talking about predictability. So it is different from making predictions, right? So in IDS, in computer science, we care about the SOTA, right? State-of-the-art model. So given a benchmark, we hope to push the limit of the prediction accuracy. But in this case, it's actually it's a very different perspective. In this way, we care about, given the system, how much, to the best. Theoretically speaking, what is the best performance out of all the possible algorithms? So it's actually quite different. So I tried very hard to try to cater these slides to try to to make it more understandable to computer scientists. But probably we can start with a very simple example. So for example, here we have a lot of IDS PhD students. So later you probably will have to pass the qualifying exam. So we have to predict, right, whether you can pass that exam. So of course, the different students have different profiles, right, different qualities. So, but we do not have the full information. So let's say that we have two students, both graduated from Tsinghua University with a GPA, for example, 3.9. That's all the information we have. And then we make a prediction whether you will pass the qualifying exam. We want to compare that, who will pass, who will not. So it's difficult, right? It's difficult to distinguish these two subjects. So this is the inherent fundamental limits in data. Of course, we may have more dimensionalities, right? So for example, for these two students, both graduated from the same college with the same cumulative GPA upon graduation. And then we have one more dimension of the data, right? So we have another feature, which is the cumulative GPA of the student after he or she joined the university. And then we have more information to separate, right, to distinguish those students. Let's say both students with the same profile before joining Hong Kong U, but the one has a very high GPA after joining the university, the other one has a low GPA after joining the university. So obviously we would predict the first student has a higher chance to pass the qualifying exam. Right, so this is a binary classification scenario, which is our first paper. I will quickly skip it, introduce that, and then we will focus on the second paper. The second paper will talk about something like more protocol-based. Here, I mentioned the term protocol. That means, in the first paper, we're mainly look into the data organization, right? Just like the PhD students passing the qualifying exams. For some of the data points, they are fundamentally indistinguishable, right? So that's all the features we have. And echoing, hello? Yeah, some mics, hello? Yeah, okay. So that's the data we have. And some data are essentially just overlapping, right? So that means they are just not distinguishable by definition. But then let's still stick to the qualifying exam question, the scenario. So here, let's say we have a lot of information of students, but then what questions we give to the students this is the so-called protocol, right? So let's say we have all the PhD students taking the qualifying exam, and we have a set of questions, but every time we pick different questions, right? Different exam papers. So there could be a chance that we happen to pick the simplest exam paper, right? Let's just assume it is extremely simple question papers, exam papers, like all the 1+1, 2+2. So that means everyone would pass the exam, right? So this is a easy to predict scenario. Another extreme question, right? Another extreme direction or extreme case is that the exam papers are super difficult, right? It's among the most difficult ones, and most of the students couldn't pass. So that's also easy to predict. But something in the middle is more heterogeneous, right? More difficult to tell. If we happen to pick one of the set of exam papers, and some student pass, some student didn't pass, their probability to pass, their chance to pass the qualifying exam is not only dependent on their own quality, but also dependent on how difficult the question papers is, right? So as I said, we have a set of exam papers, and every time we have to pick different exam papers. So theoretically speaking, whether the student can pass it is dependent on the matching between their qualities and the exam papers across all the potential exam papers, right? So this is essentially in statistical physics, we call it an ensemble, right? So there are different configurations, and each configuration indicates what questions we have in the exam papers. And there are different combinations. So there are many, many different configurations with different probabilities, right? And this probability, like who will decide which questions will appear in the qualifying exam? So that might be, like say, the committee, right? So the committee. So if it happened to be the professor who is very generous, so he is more likely to pick the simplest questions, simpler questions. So that actually determines, or this decision actually dictates the probability of students passing exam later on, right? But if these professors, the committee, they are really harsh, they may pick more difficult questions. That's another scenario, right? So you see that they're all different scenarios. But of course, the simplest scenario is we just have a random number generator and to randomly pick the questions to formulate the exam, a qualifying exam for the students. That is also a common case, right? A common case, and also relatively easier to evaluate. So from a statistical physics perspective, you can consider that there are different states, equilibrium states of the whole system. And if we happen to purely randomly pick the question papers, that's almost like we have a very high temperature of this complex system. So the the state of the system in different equilibrium states, they are similar, right? Because the high temperature will drive the system out of the equilibrium state, and there is a chance to jump to the other equilibrium states, and the high temperature will further drive it to jump, right? So in this extreme case, most of the states have similar probability. So this is more similar to the random sampling, random cases. Okay, but anyway, those are just some examples, motivating examples to motivate that predictability is actually not as simple as we have a better algorithm, right? It is also dependent on the data organization and also dependent on the protocol, which defines this prediction problem. This talk in 3 sentences. The first, which is our first paper, is data organization sets a theoretical ceiling or upper bound for binary classification. And the second, we narrow down to link prediction in complex networks. So the link prediction is harder because edges are both targets and the sources of the features. This is unique, right? So for example, in computer science, we do a lot of recommender systems. So we mask some data points, and we predict it, right? But the masking of the data doesn't change the features. But in network science, in terms of link prediction, when we mask some of the edges, it fundamentally changes how we make predictions, right? For example, the simplest method is common neighbors. So if friends is friend, right? So we make prediction based on this simple rule that if the two edges, if two nodes have a common neighbor, so we have a higher chance for these two nodes to be predicted to be positive, right? So they should have a link. But when we mask out those different links, different edges, if we happen to mask out some other edges that actually change this friends to friends, this common neighbor structure, so we also change the chance that we make the correct prediction. So this is different from the simple binary classification, right? So that's why link prediction in networks, it is harder because those changes, they are both something we try to predict. They are also the source of the features based on which we make predictions, right? And the third is that predictability depends not only on the algorithm, but also on what information is hidden, what is being compared against, and what local structure remains. Okay, so a very quick spin glass dictionary. So basically in this research, we try to map this complex system link prediction problem to a spin glass system. Spin glass system, I mean, one of our co-authors, Professor Parisi, got Nobel Prize in Physics 5 years ago. So this language of spin glass basically translates the prediction problem to a physics problem. So here is a quick mapping. So in prediction, we have the candidate rules, split rules, right? So that means, for example, like we have a group, we have those data, and we split training and testing, right? 80%, 20%, fivefold, right? The different splits, and each split that determines the configuration of the system, right? So for example, if you imagine that this is a social network, and we try to mask 10% of the connections. So every time we pick 10% randomly, right, or according to certain rules. And in that case, every time we have a different configurations, and there are just countless. There are so many such configurations. Okay, so every time we split the training, testing, and that actually defines a configuration of complex system. And the second is the success or failure in terms of predicting the ranking. Okay, so in this case, actually in both papers we focus on AUC, so that's why we focus on the ranking. When we make predictions, we have the correct predictions, the wrong predictions, of the order or of the between the actual positive cases and also versus negative cases. And this is actually can be described as the Hamiltonian of the configuration in physical system. Okay. Or Hamiltonian, we can define it in different ways, but in this case, we define it as 1 minus AOC because in physical system, the lower energy indicates the preferred states, right? More stable states, and the higher energy indicates the more difficult to predict states. So this is actually reverse, opposite to the AOC. So that's why we define the Hamiltonian as 1 minus AOC. Okay, the average AOC over all the possible configurations. Right. So this is all of the configuration space configurations in physics. It is a configuration space, and in prediction language, it is all the possible rules and the splits. Okay. Just as I said, we try to mask 20%, but this 20% it could be many different 20%, right? So that defines the whole space, configuration space in the physical system. And then is the protocol generated splits. And in this case, it actually defines like when we generate those configurations, different configurations may have different probability, right? Different chance to be generated. Let's say if we just purely random pick, in a complex, for example, like from all the positive cases, we randomly sample 10%. That is one way to generate the configuration. But if say we actually prioritize the probability of certain data to be masked, so that is a different, right? That's a different protocol to generate the split, the configuration. So here, essentially, given the protocol, right, given the defined way to generate those configurations or to split the data, so it actually defines the ensemble of all the potential configuration space and the probability of the existence of the generation of those different configurations. Okay, and then. Okay, in computer science, we chase for the best possible performance, the best prediction, right? But the upper bound, the best possible performance, it actually corresponds to the ground state or lowest energy state of the original of that ensemble. Okay, so this is a graphical, this is a visualization. Okay, the Hamiltonian assigns energy to each configuration. So you can see that here that, oops. Okay, yeah, but anyway, we have those different local minimal states. And of course, we have the ground states. And the ground states, in this case, in the prediction problem, this corresponds to the theoretical best performing, the upper bound of the prediction performance. And the others are all those different performance, prediction accuracy, or it could be the correspond to certain AOCs as they correspond to different configurations. Different configurations may have different AOCs. So here, every configuration of these complex systems has the energy value. So in physics, this Hamiltonian can be defined, can define a Boltzmann probability. Here, we also use the Boltzmann probability, but here, because it's a prediction, we use AOC most of the time. So we compare which is more likely to be predicted. So here, we use the Hamiltonian of the configuration, meaning as an energy-based ranking score or loss score, not as a full equilibrium model. We don't intend to achieve certain states, but mostly to use it to estimate the energy of different configurations and try to compare their energy. So the first paper is about the binary classification. In this case, it's very general, right? So in this case, given a feature pattern, right? For example, it's X, and of course, to make the prediction, it could be positive or negative. Right? In computer science, usually it's a binary 1 and 0. In physics, it's usually positive 1, negative 1. So belonging to one of the classes. So the px is actually the probability that it actually belongs to the positive cases or negative cases. So if the same observed pattern supports both labels, okay, if it only supports the positive, so that means it will likely give us a correct prediction. But in some cases, if the observed pattern supports both labels, right, it could be positive or it could be negative. That means they are indistinguishable, right? So we cannot separate the positive and negative cases. So in this case, no classifier can remove the ambiguity. So therefore, even a perfect classifier has a ceiling imposed by the data overlap, just like the qualifying example that I introduced at the beginning, right? So we only know that these two students have exactly the same profile. So of course, we cannot make the correct prediction. So I skip a lot of the technical details, but in general here, we focus on the AUC of the ROC as the main results. So you know that ROC usually is, it is a convex function. So we can actually start with the formulation of the AOC so that we can easily prove the theoretical optimal AOC given the data. Okay, that was what we did. And then we did, of course, a lot of empirical analysis with different data. So here we did validate that the data overlap sets a classifier independent ceiling. So this is first paper. It has not been published. We still, we got unlucky for the first paper. But the remaining gap asks whether the protocol exposed a recoverable signal, right? So that's exactly what I have been trying to say that. At the beginning, it's a data organization. But the second question is, given this data organization, given the masking protocol, do we have enough signals to recover, to make the correct prediction? And that is the second paper. So the first paper is just a binary classification. So it's mostly the tabular data. So, so here we hide the labels, right? We hide labels, whether this student pass or not, okay? But this leaves the feature intact, right? So this is a Tsinghua undergrad, 3.9 GPA, and he passed or he didn't pass, whatever, right? So the feature didn't change. But in network data, the feature may change itself. So the edges are both the prediction targets and also the source of the structure features, right? The simplest example still, it is the common neighbors or some path-based algorithms, or it could be, let's say, degree-based prediction, right? We mask out some of the edges. That changed the common neighbor structure. That changed the degree of some nodes. That also changed the distance between different edges. And all those are the features that we rely on to make predictions. Okay, so that is why network data is more difficult. So the takeaway message here is that in link prediction, evaluation itself perturbs the topology that we use to compute the features. So a very important note here is that link prediction is not equal to binary classification. Actually, before we started this research, I also think that link prediction is just a binary classification, and then I realized that it's actually different. And this is just a spin glass model illustration because we try to use the spin glass model and also the following caveat methods to address this problem. This is just give a quick illustration. So we probably just focus on the top three, okay, the top three figures. The panel A, this is a simple toy example. We have 4 nodes and 4 edges. And one edge has been masked, which is the edge 2, 3, okay? And the remaining 3 edges, they still remains. So here, the 1, 2, 1, 4, and 3, 4, they still remains. Those are the 3 remain edges. And then we try to make predictions, right? We want to predict whether 2 and 3 has a connection. Let's say we assume, let's say in this case, we rely on common neighbors. So in order to predict if 2 and 3 has a connection through common neighbors, so we have to look into the neighbors of 2 and 3. So that's why we have to look, we have to rely on the existence of edge 1, 2, the existence of edge 3, 4, right? So these two edges to give us information whether there exists, this edge should exist, right? So this is a simple illustration. But also, right, in this case, we have to compare the score we give to 2, 3 versus the score we give to negative sample. Negative samples indicates the edges that should not exist in the first place. The non-existent samples, for example, 2, 4 and 1, 3. So in this case, you see that the 2, 4 is here. It depends on the 2 and 4. So that depends on their connection to node 1 and node 3. And the connections between 1 and 3, that depends on their connections to V2 and V4. So that also illustrated here, right? So this is just a common, this is a toy example to demonstrate that in order to make predictions of certain edges, no matter whether it is the true but mask the edges, or it is non-existent edges, those are the information we rely on, okay? So you can imagine that if in some cases, if this edge is also disappeared, so some of the prediction, the features are different, right? So that's one thing we try to argue. And then we use a spin glass language. So spin glass language, and that means we assign the spin directions, positive 1 or negative 1, and to compute the energy for different configurations, and eventually use those information to calculate the Hamiltonian, and eventually we take the average of all the configurations and to derive the predictability of this whole system, given the masking protocol and given the negative sample methods, and also given some other features. So in general, this is we can consider this masking experiment as an exam for the networks. So first, we have a full network with all the observed links. And then we mask, right? We hide some links. And those edges, which were hidden here, are something we want to predict, right? And then we define the scoring methods, scoring rules like common neighbors or some other methods, using the remaining graph, right? Because some edges are already gone. So we have to rely on the remaining graph, which means incomplete features to make predictions. Okay, so the final predictability is also dependent on the scoring method. And then we have to compare the score we obtained for the true but masked edges versus non-existent edges at the very beginning. Okay, so the takeaway message for this is that one masking split is we can consider it as one exam, like the quantifier exam, and predictability actually asks how well the network passes these exams on average. It's like we take out all the exams we prepared for the qualifying exam, and how did this perform, how our student perform on all those possible exams, and then the average, right? But so you can imagine that how the probability of different exams to be present to our students depends on how we pick those exams, right? I picked so different probability. Alec picked it different probability, or just a random number to pick it, the uniform probability, right? So that's just different protocols. So this actually gave another smaller and easier to understand example that when we mask certain edges, this caused the structural perturbation, and this masking actually changed the probability, right? So here, let's say those two are the real edges that are masked. And then we try to predict, let's say we try to predict the probability of I and V are connected based on common neighbors. So, right, so previously there is a common neighbor of I, right? So for J and V, so supposedly it's a friends is more likely to be friends, so we can make a correct prediction. But because this edge has also been masked, so we lost this information. So I, J, and V, they don't have common neighbors. So if we use common neighbor to make prediction, we wouldn't predict these two edges to be connected. Well, on the other hand, right, so the negative sample, of course, we can pick very different negative samples. Some negative samples are just very unreal, so it cannot be predicted. But here, I picked a more difficult negative sample. You see that we want to predict V and U. They do have a common neighbor, and these common neighbors were not masked. So in this case, the model based on common neighbor, either deterministic common neighbors or common neighbor-based deep learning models, right? So they will automatically assign a higher score for U and V. So that will give us very different results, right? So that actually determines the theoretical upper bound of the prediction performance, right? So because we mask, right? So we mask some edges. So we change the topology. Because we change the topology, some common neighbors may disappear. Some shortest passes may disappear. Some degrees may got changed. So those are degree and the community signals, they actually shift. Let's say, let's imagine we have another algorithm to predict based on the shortest path length between two nodes. And we have two communities, and there's one bridge in the middle. And what if the edges connecting two communities got masked? And suddenly, those edges, those nodes in two different communities, they become almost impossible to connect. The shortest path length became so long. So that will change the whole predictability of a whole set of the network. So you see that those are different. So in this case, you can sense one thing is that the predictability of the whole network is actually dependent on the predictability of certain edges. So this actually gives us the hint that later we want to decompose, right? We want to decompose the overall whole system predictability to local predictabilities of certain subgraphs and certain edges. So the takeaway message here, in networks, the label split is not only it's not only just to split training and testing, but also it is a structural perturbation, the changes to the topology. So in this case, in the link prediction in complex networks cases, the AOC is actually a pairwise ranking test, right? Essentially, we're asking, we're actually setting the scores, right? We're asking if the true but the hidden edges have a higher score than that of a non-existent edge, right? If that's the case, we have one score. If it is tied, we have a 1/2. So in this case, right? So we have the hidden true link, hidden true edge, and the non-existent edge, and we have the E and the E bar. So eventually, this lowercase e indicates the true but the masked edges or link, and the score for it, for like a common neighbor or something. And the non-existent link or non-existent edges, we denote as E bar, and also we have the score. And eventually we'll compare these two scores, right? We'll have to see how often, how likely the score SE is larger than score SE bar. Okay, so that is, so in this case, the AOC is not that mysterious. It is actually the chance that a real hidden link or edge is ranked above a fake negative candidate. And also the masking protocols, right? So here in this language, we have that full network, but the edges will be split, right? We have to select a subset of all the edges to mask. So here the capital ER means the edges that remained visible. And the capital EM, that means that indicates the edges that were masked or missing. Of course, they have to be mutually exclusive. So here the predictor scores. Here the predictor, like common neighbors or or GNN, right, or different methods. Those methods they score using only the remaining graph, right? So because some are missing, so all the prediction are based on the remaining graphs. So there is no missing graph. The remaining edges, there's no missing edges. So this is just a reformulation of the AOC formula. So the takeaway message for this slide is that for a given split, The AOC is the probability that the missing true edge receive a higher score than the non-edge, plus half of the probability for the type. Okay, and then let's consider those individual edges. Okay, so individual edges, we'll have to define that local configuration for it, sigma. So if it belongs to the missing edges, that means something we want to predict. So we give it a positive 1. If it belongs to the remaining edges, so we give it a negative 1. Okay, so of course we can change it to 1 and 0, but this is just for computation facilities following that spin glass language. So how many configurations we may have, right? If all the edges can be masked. So in this case, we have 2 to the power of m, right? So capital M, so that's just a lot. And in most of the cases, we randomly mask a proportion of the edges, right? So out of all the capital M edges, we mask a small case m. So that's the choose, the small case m from the capital M. So that's the number of configurations we have to average, right? And this average is not uniformly average. It's averaging over the probability of the appearance of those different the occurrence of those different configurations. And as I indicated at the beginning, because in in physics language, the Hamiltonian, the lower the better. But in prediction language, the AOC, the higher the better. So the Hamiltonian is now here we define it as 1 minus AOC. Of course, we can also just make it equal to AOC, but just following some, we have to just have to be consistent. It doesn't matter. And this Hamiltonian, according to the probability, we have that average. And this probability usually is a Boltzmann distribution. And AOC, of course, is also based on the Boltzmann distribution, the probability of that existence of that configurations. So under this convention, the ensemble predictability is satisfied that here we have a term gamma as the predictability is actually 1 minus the average of the Hamiltonian. So here the Hamiltonian simply means the prediction loss, right, for this case, because we want it to be lower. So it is a prediction loss for one masking split. And we have different split, so we have to average it, right? So we chose a loss-like convention here, so the larger Hamiltonian means the harder recovery. And here, to define the actual predictability, it depends on 3 choices. One is the scoring rules, like I mentioned, the common neighbors stuff. The S and R is the masking rules, and also Q is the negative sample, the peak of the negative non-existent edges to compare. So any change to any of these, we are measuring a different predictability. Okay, so this equation is different from our paper. Just try to make it more intuitive. So essentially, this predictability of the graph G is dependent on the scoring rules, is dependent on the masking protocol, and also dependent on the negative sampling method. And here in the equation, that indicator theta just tests whether the score of the true hidden edge beats the score of the negative candidate. Okay, of course, right, so here, the masking, right? The masking, we have different masking methods. The simplest one could be just the Bernoulli masking, right? So every edge has the exact same probability to be masked. That's the simplest one. Also, this equation indicates. But of course, there are different, right? So it could be fixed size masking. It could be degree-based masking. Let's say, for example, like a higher degree, the higher chance the edges got masked. Or, as I mentioned, that the bridges, the brokers between 2 different communities, that could be also something we want to mask, right? So this is more related to the downstream applications. Let's say if this is cybersecurity stuff, we want to attack something. Or this is the treatment. We use the drug to perturbate the cell, right? So we probably want to highlight something with a higher chance, like the bridges or something. And of course, there could be some temporal masking here. So the takeaway message for this is that different masking protocols induce different distributions. And this one is for the Bernoulli case. But if we use different masking methods, we have different configurations. We have different probabilities for each configurations. Okay. The last piece is the negative sampling. Here I have a simple example, right? So if in this case this is for like a radiology task, we want to compare the CT report, CT image of a cancer patient and a healthy control. It's easy, right? This is really easy, but it is easier. But another case is more difficult. Is that we compare a case of an early cancer patient versus the benign nodules. Okay, in this case, both of the subject have the nodules, but one is early cancer. It's not that obvious, and the other is benign nodules. It's also not that obvious. So in this case, the negative class defines scientific difficulty. So in our cases, the same thing, right? So in the network science community, let's say we have a real community, and now we want to compare. Let's see. For example, we try to predict the friendship between PhD students. So the two students in the same department, they are more likely to have a friendship, right? So, but of course, a lot of students in the same department, they don't know each other. So if we, in our problem, we try to compare the masked relationships against those kind of non-existent friendship in the same department. So this is more difficult, right? As compared to, we randomly pick two students from Hong Kong U. So it could be two different faculties of the students. So those are relatively easier than comparing to two students who don't know each other in the same department. So this is essentially the Q here. Right? So Q determines how we sample the negative cases. And so this is the general formulation of the problem. But we find that the network is usually very complicated and give us too many configurations to average against. So we figure out that we can rely on the local cavity. Local cavity, that means the local nodes, local edges, and the local neighborhoods. So we only look at local neighborhoods. For a lot of the algorithms, this also depends on the scoring rules, right? For example, if just the common neighbors, so it's entirely local connectivity driven prediction, right? But for some other cases, for example, if we're talking about using the GCN or some other deep learning approaches that consider global connectivity, so that will make these methods less relevant. But of course, it is approximation of the overall cases. So here, the target edge stays hidden, but the recoverable signals comes from the survival local support motifs. Here, the motif is just subgraph, okay. And it is evaluated against those negative cases. Okay, so this is just one example. Okay, right. So this is again the local connectivity got changed, but the far away connections may not matter here for the scoring of these two edges, right? Because here we only rely on some local connectivity. And actually, of course, for a lot of the methods, the prediction methods, it is totally local based. For some of the methods, it's not local based, but it can be approximately decomposed to some local based scores. We will lose some accuracy, of course, but we will largely reduce the computation complexity. So this also gives us some heuristics for the future, like deep learning prediction algorithm design, right? But in general, we use the cavity methods to look at the local connectivity of the edges at risk, of interest, so that we can decompose the energy estimation of the whole system to actually those additive local connectivities. Okay, so in this case, for the local scores, only the nearby supporting motifs around the target edges, they actually matters, but the distinct, far away masked edges are largely irrelevant to the local score, so that we can decompose, right? We can decompose. So we actually have an algorithm to try to achieve the optimal solution here. Okay, but probably running too long. But here, eventually, we have this prediction index. So averaged over the AOC. We have the gamma zero that denotes estimated performance limits. That's the best among all the configurations. So if this gamma, okay, if this gamma is high, that means a lot of the recoverable structural signals still exist in the remaining graph. If it is low, that there's little discriminative signals existing in the remaining graph. And of course, the algorithm gap, right? So if given a problem, we find that there is a significant gap between the model's performance and the theoretical upper bound. That means we probably want to change the algorithm. If they are already close, that probably means that we don't want to waste additional resources on it. Here, we actually test the different algorithms. The different curves indicates different algorithms. You see that different algorithms perform very differently. For some of the algorithms, the more we mask, the worse. The worse they can predict. But for some, the more we mask, the better they can predict. So different algorithms actually behave very differently on different data sets. So this will give us the guidance, right? It's not a beacon, but something to guide us through what kind of models we want to use for different data, how we want to change our model or improve our models. So this is naturally suitable for those local connectivities, but for some global embeddings like deep learning approaches, we have to check whether how much the connectivity can be decomposed to local ones. So in this case, basically we replace the global illumination by local effective signal estimation. And we tested on some synthetic data set and also some empirical data sets. But in general, the different generative structures respond very differently on this edge perturbation. And to summarize, okay, so to compare the two papers I introduced here, why the second paper is more mechanistic? Because the first paper is only looking at the data organization, right? So how the data looks like, but it didn't consider how we formulate that prediction problem. But in the second paper, we try to move beyond just the data organization, but it's a more specific link prediction problem. It is dependent on the protocol of how we mask the data, how we sample the negative cases, etc. Right? So eventually, this narrow scope gives us a deeper mechanism understanding of these link prediction problems. The last slide, to go beyond the predictability of that binary classifications or the complex networks, complex system is not only about the network structure, right? Of course, network structure is the natural representation of the system. But this system may be dynamic, right? So there are dynamical processes over time series data, and also it has very different applications in various different fields. So that actually give us, actually we have to work on several things. One thing is our current method is mostly on local connectivity. We have to extend it to global connectivity methods. And also, it is static network, right? You can sense that this so-called link prediction problem is more like a network reconstruction problem, but it's different from like predicting temporal prediction, right? To predict future connections. The future connections that will be more related to generative models. So how we can extend this theory to generative models, that's also something we hope to work on in the future. But in general, the take-home message, predictability here tells us whether improvement is still possible and where new theory is actually much needed. And also it gave us the heuristics or the hints of how we can design. In this pursuit of that new theory, we may have a new theory to, in turn, guide us how to design a better prediction model. Okay, and there is a recent review in Physical Reports. They gave a field level horizon and also the summary of the research in the predictability so far. Okay, so those are the two papers I mentioned, and also the more recent review papers for your reference. Okay, thank you.
Thank you. Oh. All right. So we still have, I guess, about 8 minutes. Does anybody have any questions?
Yeah, very interesting talk. So, because I work in machine learning, so I wonder whether we can also put this notion of predictability into, let's say, deep learning systems. Like, for example, we are given a set of like complex image classification data, and we would like to study whether the system, like certain kind of system performance is still improvable or not, or let's say the current large language model type of thing. We also apply such kind of study on top of that. And what do you think, and what kind of new technique do we need for that?
Oh, thank you for the question. In our first paper, pretty much focus on this problem. But of course, it's only for the binary classification. But at least for the binary classification, for example, this is a picture. We want to predict if this is a dog or not. You can use our method to quantify it. But this quantification would be based on we have to extend all the dimensionalities. In the qualifier example, that's only 2 or 3 features. But in a computer vision problem, there could be hundreds or thousands or tens of thousands or even millions of the dimensionalities. That will make the whole, actually I would say for some of the cases, the upper bound is theoretically close to 100% because those 2 pictures, they are essentially no overlapping at all. But that's only a very general theoretical upper bound, but it didn't give us the guidance about how to achieve that. Well, in the second paper, although this is for networks, the link prediction in the networks, but at least we link it to how we mask the data, how we select the sample, negative samples for the experiments. So that may give us some insights into like even in the CV problems that also like when we design a problem, when we compute the accuracy, I mean how we sample some negative cases to compare, and for those positive cases, how we select them to be the training and testing. So those are the common practice that may still apply to a more complex scenario. But I have to admit that that's much more complicated than the link prediction. The link prediction, we can simply address it by matrix decomposition. It's just basically a matrix. But for computer vision problems, of course, that is a matrix, but it has much more dimensionality here. So whether we can extend it and still the theory holds, we haven't tried it, but that's definitely something we hope to pursue in the future.
Yeah, thanks.
Yeah, thanks.
Any other questions? One thing I was curious about, I guess, I'm not entirely sure that it's sort of statistical physics rather than like averaging the AUC. I guess the reason is because in statistical physics, we would use the Hamiltonian to define the probability distribution. Yeah. So it'd be like a Boltzmann distribution in this case. I guess if you were looking at the uniform distribution.
In the slides, it's based on the uniform distribution.
So it's just like it's like an infinite temperature limit.
Right.
Okay,
So in that case, the temperature is like the infinite high temperature. Mm-hmm. Yeah, in that case, because it's random. Yeah.
Okay. So I guess one thing that might be interesting, I don't know if you tried this, but like if you defined the AUC as the Hamiltonian, then if you just tried to find the ground state, then I guess you had mentioned this, but I'm not sure if it was presented in the results, like to find the kind of configuration of holdouts that give you the best performance. So it's kind of like a way to cheat with your like predictability. So that might be something that's like interesting to try, is to just use the AUC as the actual Hamiltonian and then lower the temperature until you get to a ground state. It's going to be hard because like any of these problems, it's hard to find a ground state, but it could be interesting. And then I guess the other thing I was going to ask is, how did you compute the averages? Like, were you able to estimate the average energies using some sort of like variational technique? Because you mentioned cavity method, but like I didn't see like what the variational approximation was. Or did you use like Monte Carlo sampling for the?
We actually tried different approaches. And we listed the more detailed results in the supplementary materials. But we did try those sampling-based approaches and also the approximation-based approaches.
Okay.
Yeah.
Cool. I think I also saw a question on this. Does anybody else in the audience have any questions? Okay, so I have one question here. Was this from the Zoom? Okay. So it says, thanks, Professor Zhang. You mentioned that predictability depends not only on the algorithm, but also on the masking and negative sample protocol. In applications, how should researchers choose or justify these protocols to make fair comparisons between prediction methods? So I think you've talked a little bit about this, but maybe you can expand a bit.
Right. So we haven't done that research yet, but just from the empirical results, we did find that different algorithms have kind of different behaviors. For some algorithms, of course, it also depends on the masking protocols. Let's say if it's just random masking, for some algorithms, the more you mask, the more predictable. But for some algorithms, the more the mask, the less is predictable. So we may, at least theoretically or empirically, we can derive some of these patterns as some sort of a guidance, right? And then we can try to correlate this to some of the real problems, at least to give some empirical guidance that certain methods might work better. But of course, in our paper, we only tested those local connectivity-based link prediction algorithm, like a common neighbor stuff. That's relatively simple. But those are also useful heuristics for us to design the deep learning-based approaches. So I would assume that those knowledge can be transferable to some of the design of deep learning-based prediction approaches.
Awesome, thank you. Okay, so I guess let's give Professor Zhang another round of applause.
Thank you.
And we'll do some group photos as well. So if we could have everybody kind of like concentrate towards the center.